Hello, calculus fans. Back in one variable calculus, we talked about moments and centers of mass. We were able to compute the center of mass of a lamina with constant mass density. We're now going to do it for a lamina with variable density. So let's suppose we have a lamina that occupies some region with a mass density function rho. So that tells you how much mass is in this object at any particular point, mass per unit area. Now remember that we define the moment of a particle about an axis to be the product of its mass and its directed distance from the axis. This is based on Archimedes' law of the lever. And the principle is understood by grade school children with a seesaw or a teeter-totter. If you're the big kid, then you have to be closer to the fulcrum. And if you're a smaller kid, you have to be farther away from the fulcrum in order to get the seesaw or teeter-totter to balance. So we do the same sort of thing that we've been doing all along. We'll divide D into small rectangles, and then the mass of one small rectangle is approximately rho of xjk star yjk star delta A. And again, we have appropriately chosen sample points in each subrectangle. So we can approximate the moment of a small rectangle with respect to the x-axis using the mass times the distance. The distance is going to be y sub jk star. And same game as always, we add these quantities, take a limit, and when we do that, we get an integral that represents the moment of the entire lamina about the x-axis. So here's the formula that we get. This integral formula will tell us the moment about the x-axis of the lamina. So we write mx for the moment about the x-axis. It's just going to be the double integral of y times the density function. And we can do the same kind of thing to get the moment about the y-axis. Now we're going to get a double integral of x times the mass density function. And just like we did in one variable calculus, we're going to define the center of mass, x bar, y bar, so that the total mass times x bar is equal to the moment about the y-axis, and mass times y bar is equal to the moment about the x-axis. And the physical significance here is that the lamina will behave in terms of balancing as if the entire mass was concentrated right at its center of mass. So this thing will balance when it's supported right at the center of mass. Let's summarize all of this in a theorem. So the theorem gives us a way to compute the coordinates of the center of mass of a lamina that occupies some region D and has mass density function rho of xy. So the formulas are that x bar is equal to the moment about the y-axis divided by m. And we showed you before that the moment about the y-axis can be computed with a double integral of x times the mass density function. Y bar, everything is backwards now, y bar is the moment about the x-axis divided by the mass. And the mass can be computed simply with the double integral of the mass density function over the region in question. And then we'll show in a bit now how to use this to actually compute the center of mass of some region. Remember that the key here that what we're doing differently is that we're allowing us to have a mass density function which specifies in a way maybe the thickness of the metal plate or the whatever object we're trying to compute the center of mass of. And if the mass density was constant, then a lot of the things could have been accomplished using the techniques that we learned in one variable calculus. Okay, that is all for now.